screenshot that. So this is section 3A, number 8. There we go. So we need to apply implicit differentiation. So we differentiate each side independently. That left side's last. What's the derivative of the left side? 5. Love that. Right side's probably where the fun begins. All right, so we have both the chain rule and the product rule going on there. So I'm going to do this one in stages. The outer function is what? The outer function is the sine of x. The inner function is that y times x times y to the 6. So derivative of the outer function is just the cosine. And then you leave the inside the same. Then the fun begins because we have to take the derivative of the inner function. And that's where the product rule comes in. So I'm going to throw in extra parentheses to multiply, and the derivative of x is 1. The y function stays below the way it was for a moment. And then I'm going to add on x times the derivative of y to the 6th, which would be 6y to the 5th, y prime. That makes sense, so I get that. All right. So from here, my goal is to, I think, solve for y prime, and then I'm going to find y dx. Yep, find dy dx. I have two options. I could break this multiplication of the cosine by dividing by the cosine, or I could distribute it through. Yep.
Can I write on the test? Can I write dy dx instead of y prime?
Yeah, you can write dy dx.
It really helps my brain.
Yeah, the main reason I wrote y prime right there is because I was running out of room. But I like dy dx too. So I'm going to choose to divide by the cosine rather than distribute. So then I get 5 over the cosine of xy to the 6th equals y to the 6th plus x, what's that, times 6 times y to the 5th times y prime. Again, I want to get y prime alone, so I think my next choice would be to subtract that over to the left side. So then that's going to give me 5 over cosine xy to the 6th minus y to the 6th. Equals, I'm going to reorder those terms just a little bit. I'm going to write it as 6 times x times y to the 5th times y prime. So last step, y prime is just being multiplied by a bunch of stuff. So to get rid of it, I'm going to divide by it. And that's in the window. All so. So for this might be the last step. I'm just going to divide by 6x y to the 5th. And then I have on the top this complex fraction. And we could apply some algebra, but it's not going to simplify much. I think it'll just use marginally less ink. So I'm just going to stop there. Depending on your choices in the way you solve this, there's going to be variations on that. Yeah.
Does 5 over cosine xy to the 6th become 5 secant xy to the 6th?
You could write it as 5 secant because 1 over cosine is secant. Okay. Yeah, but I don't know if that makes it any better.
Well, then we don't have that lovely fraction on the top.
That's true. We would get rid of the fraction on the top. Yeah, I'm going to stop there. I'm going to say that's my answer. So let's see if the computer likes it. I think it will. I can remember it all. So lots of parentheses here. 5 over cosine x y raised to the 6th minus, I forgot,
Right.
y to the 6th again. Let's see, where am I? Right here. Minus y raised to the 6th. Close the numerator, divide, parentheses for the denominator, 6x y raised to the 5th, I believe is what was down there. I look right?
Mm-hmm.
I think so. All right, see if we get a yay on that. Yay.
Wait, can you click show answer real quick?
Yeah, so they took the approach where they distributed the cosine through, and that where I got divided by it. Yeah, and you could, another way to get from that to my answer is you could multiply top and bottom here by cosine xy to the 6th. That would give you the same result. But I don't mind the complex fraction in this case. Yeah, so again, depending on the algebraic route you took, there's variations on this answer. That's one right version. All right, let's see. There was a question on number 6. That one is just, you got to be super careful with algebra. So I'm going to get it set up, but I don't think I'm going to do the entire thing.
Yeah, I did spend like half an hour the first time.
It's
I
a
got it wrong, but it turned out I just had an x
little tiny error.
I didn't.
instead of an x squared in one spot.
Yeah.
I didn't notice that the 2x squared plus y squared. I didn't notice that parenthesis was squared. Like there was like the extra square outside the parenthesis.
That extra square right there. Yeah. Okay. So implicit differentiation. So I'm just going to get this started and tell you how the best way to continue is. So I need the derivative with respect to x. The left side is the harder side. 2 times x squared, so let's just do a plus, y squared squared. So we're going to have the power rule there and the chain rule. On the other side, derivative with respect to x of 25 x squared minus y squared. And I'm going to have to write the results on 2 different lines because this is going to get kind of big. So let's see, this 2 right here is just hanging out. And then applying the power rule, because that's the outer function, I'm going to get 2 times the base to the power of 1. Right? We drop that power by 1. But then we have to multiply by the derivative of the inside. The curly bracket for that multiplication. So let's see, the derivative of x squared is 2x. And the derivative of y squared is what?
2y.
2y prime, or 2y dy dx. And then, so that's the left side. And then I have to do the right side, which isn't too bad. On the right side, the 25 just hangs out. And it's going to be multiplied by the derivative of 2x, which is, so use parentheses, 2x minus 2y dy dx. So there's the left and right sides. So just some things to note. The power 1 is kind of not all that meaningful, so I'm just going to erase that there. And you don't have much choice here but to distribute on the left side. So there's going to be a multiple of 4 that's going to have to get in there, and then you have to distribute those 2 terms to those 2 terms. All right, what's our goal here?
Get y prime itself.
Okay, so it's not just to get y prime here.
Because it's the solve of the point.
Here, we want to find the derivative at a point. So what I would do at this, since they don't actually ask for dy dx, they just ask for the slope. At this point, I would just plug in -3 and 1, and this simplifies dramatically. Yeah.
Mm-hmm.
Yeah.
Then you want to do all whole numbers.
So note x equals -3, y equals 1. Just go drop those things in here. So if I do that, I'm going to get 4 times -3 squared is 9 plus 1 squared times 2 times -3 is -6 plus 2 times 1 is 2 dy dx equals 25 times, let's see this wrong way, -6 minus 2 dy dx. Yeah, and then you just have to do a little arithmetic to finish this up. Distribute the 4, distribute the 25. I'm going to leave it at that. So that's the way I'd recommend doing this.
So if it doesn't ask for specifically dy dx,
You can just plug in as soon as you do as soon as you get your initial differentiation done, just plug in and do arithmetic from there. Yeah, and well, you have to do a little algebra, but way less algebra. Yeah, what's up?
can we do yes.
Sure. Number 9, yes, we'll do the pretty much same idea on this one. We'll get an initial derivative. We won't worry about cleaning it up or solving for dy dx, and we'll just plug in the values there. So let me get a new page here. Screenshot the necessary information. Actually, we'll just do it one at a time. So the point is 1/4. So I'm just going to make a note up here. X equals 1, y equals 4/9 once we get a derivative. Hey, Raphael. So implicit differentiation. I need to take the derivative with respect to x to this side and the derivative with respect to x of that side. So on the left side, I've got to use the quotient rule. Yeah. So we have low d high, so that's going to give me y times the derivative of the bottom. Oh, no, wait. Low d high, write that backwards. Oops. Low d high, what's the derivative of y?
0.
Y prime. Yeah. Derivative, if it was x, it would be a 1. For y, it would be 1 y prime. So I'm just going to call that dy dx. You can call it y prime if you like. It's a y there. So then I have to go minus high d low. And d low is going to give me a 1 minus 2 dy dx. Yeah, derivative of x is 1. The derivative of 2y is 2 times, the chain rule says, dy dx for y prime. Other side's pretty straightforward. I just get 8x to the 7th on the other side. So then we just have to clean this up and collect dy dx's. We have to distribute.
Why can't we just plug x and y in from there?
Oh, right, yes, that was the goal. Thank you for reminding me. Yes, we don't have to find dy dx, we just need a slope. Yeah, so just go plug in the 1 and the 4/9. So then I'm going to get 1 minus 2 times 4/9. So I can just call that 8/9 if that's okay. On a test, it's probably worth writing 2 times 4/9 to be extra careful. So 2 times 4/9 is 8/9. Dy dx minus 4/9 times 1 minus 2 dy dx. Not much happens there. Equals 8.
What happened to the low squared?
What happened to what?
Low squared.
Oh, shit. You're right. We forgot low squared. Everything. Ooh, so close. We forgot low squared, or at least I did. So all of that has to be divided by x minus 2y squared. So down here, that would be a 1 minus 8/9 squared. And we just carefully do that arithmetic, then do a little bit of algebra. You guys okay from here? Okay. All right, moving on to 3.9. through 20. All right. Oh yes, logarithmic differentiation. Excellent.
What number is this?
This is number 18. And 3.9. So the way logarithmic differentiation works is you take the logarithm of each side. So that gives me the natural log of y equals the natural log of 1 plus x to the power of 1 over x. Because the problem with the initial function is I have x in the base and x in the power. So neither the product rule or neither the power rule nor the exponential rule applies here. Because the power rule says the variable has to be, the power rule says the power has to be a number, and the exponential rule says the base has to be just a number. And we have a variable in both places.
So you just ln both sides, right?
I use L on both sides, yeah. Yeah, so whatever you do to the left, you gotta do the right. So here I'm just taking the natural log of both sides. Logarithms have a lovely trick in that if you have the logarithm of a power, you can bring that power out as a multiple. So the left side becomes 1 over x times the natural log of 1 plus x. And so the logarithm allows me to get the power down, and so I can use the product rule instead, is the trick. So now we just implicitly differentiate on both sides. So derivative with respect to x there, derivative with respect to x there. Derivative of the natural log, 1 over, yeah, so that's going to be a 1 over y, but then the chain rule says I have to multiply by dy dx or y prime. Your choice. Other side, I have to apply the product rule. So the derivative of 1 over x, you could treat that as x to the negative 1. You're going to get negative x to the negative 2. Leave the other function alone for a moment. Then add, leave the first function alone, and multiply by the derivative of the second function. The derivative of the logarithm is 1 over whatever was inside, so 1 over 1 plus x. Chain rule says you got to multiply by the derivative of 1 plus x, which is
1.
1. It's just 1. Yeah, so there's kind of boring times 1. Now, fortunately, there's only a dy dx on the left
I have a
side.
question.
Yeah.
How, where'd you get that negative x to
Where it's
the,
Yeah, so that's the derivative of 1 over x. If you treat 1 over x as x to the negative 1.
okay, but, oh, to the negative 1, okay,
Yeah,
no, I got it now.
With me. Yeah, so I just applied the power rule to that. So
Okay,
I get negative 1 times x to the negative 2. Other questions on where I am now? Okay, so how do I get dy dx alone here?
Multiply by y.
Multiply by y. So then I'm going to get dy dx equals y times all of that stuff. Now, what is y really? It's that. So I'm just going to write that down instead of a y. And so my y is 1 plus x to the power of 1 over x. And then I have to multiply times all of this stuff. And that doesn't really clean up too much. If I want to write it in a similar manner to what I have here, I might call this term right here 1 over x squared. So I'm going to say
Negative
that's
1
the
over x.
opposite of the logarithm over x squared. So that's this stuff right there. I don't see the point in distributing those, but I'm going to put them in a single denominator. So that would just be 1 over x times 1 plus x. And you could distribute that the x through there if you want. But it doesn't get much prettier than that. So because on the left side we have the natural log of y, the derivative of the natural log is always 1 over whatever you had there. You're always on the left side going to get a 1 over y dy dx. So then the answers when you do logarithmic differentiation are always going to look like the original function times whatever happened on the other side. That's the way it's always going to work out. But we can't do this derivative without it. I don't know anybody that could apply the definition of the derivative to that and successfully complete it. There might be a couple of people in the world. Okay, maybe a dozen people could do that. All right, moving on. Where are we? 19. So this tan H, you've probably not seen before, so my hope was you would all click on the video. Anyone click on the video? Okay, and the video just says what hyperbolic tangent means. So all hyperbolic functions are a collection of e to the x's in a certain way. So we just got to look up which one that is. Okay. So.
Are you going to put one of those on the test?
Am I?
I mean, we have to look it up.
Yeah, I would give you the formula. Yeah. So if you look at the sample test. Let's see, where did I put that? I put it at Harris's. Yeah. Stop it. I gave you one of those on the sample test. This function right here is the hyperbolic sign of 3x. Yeah, I give you the e version instead.
Oh, okay.
Yeah. Yeah. So if I put that on the test, I would give you the e version.
Okay. Just making sure.
Yeah. So let's just look up that hyperbolic trig functions. And Wikipedia is always a good place to go.
The only teacher I know that likes Wikipedia.
That's crazy. Wikipedia is an amazing place. So here's the different definitions of them. We have the hyperbolic tangent, is that right?
Yeah.
Of 9x, yeah. So we want the hyperbolic tangent formula. And there's a bunch of different ones. Oops, whoa, what did I do? Here, guys, I blew it up too much. I don't know which one's the better one. This one, or that one, or that one.
Just plug it in.
I think I'm going to go with this one right here. Yeah. William, what's up?
Would hyperbolic tangent be hyperbolic secant squared
Its derivative?
inverse derivative?
That is a good question. I do not remember all the hyperbolic derivatives off the top of my head. I would have to look that up.
I think it's different because
It could be.
Well, let's look at
Yeah, well, these are the functions, not the derivatives. Yeah, so William's saying, would the derivative of this be the hyperbolic secant squared? And it may be. We're going to find out right now. So let's see. I'm going to screenshot that. Where's my whiteboard?
Let's do the.
Uh-oh. My whiteboard disappeared. Oh, there it is.
Motion.
My tools disappeared. There they are. All right, so I'm going to grab this version right here. So that right there is what they call tan h of x. We want tan h of 9x. So the hyperbolic tangent of 9x is just put a 9 into the x there. So e to the 9x plus e to the negative 9x over e to the 9x minus e to the negative 9x. And then to take the derivative here, we just have to apply the quotient rule.
Well, don't we also have to multiply by 9? Or skipping?
That's just going to come out when we do the rule. So we're going to get the derivative with respect to x of the hyperbolic tangent of 9x. And so we want at the bottom e to the 9x minus e to the negative 9x times the derivative of the top. So what's the derivative of e to the 9x?
E to the negative.
Almost 9 e to the
E to the
9x. Because we get the chain rule says if that's anything but an x up there, you're going to multiply by its derivative. So that's going to give me a 9 e to the 9x. And then what's the derivative of e to the negative 9x?
Negative 9.
Negative 9 times e to the negative 9x. So that's going to be a minus 9 e to the negative 9x. And I am swiftly running out of room, so I'm going to bring that down to a new line, I think.
I just need smaller.
This is a little bit of a dilemma. Let's see, let's move, oh shit. Okay. Anyway, I guess I'm not going to move it. So then I have to do minus, leave the top alone this time, so e to the 9x plus e to the negative 9x, and then multiply by the derivative of the bottom, which is going to be 9e to the 9x. And then here I'm going to have minus a negative 9, so it's going to be plus 9e to the 9x.
That'd be negative 9.
It's going to be minus a negative 9 there.
Yeah, but when you
Yeah, on
apply
the-
x.
Oh, did I miss
equals
the negative? Oops, nope, I missed the negative. Yep, thank you. Good job. And then this is my numerator here. So all of that is divided by the square of the bottom. So e to the 9x minus e to the negative 9x squared.
That looks.
Okay, so can we clean this up?
Why?
Why would we clean it up? Just for fun. Let's see.
Looks painful.
Maybe true.
Yeah, I guess we need to distribute.
We take out.
Really?
3x,
What?
we
Yeah.
have 9x.
In the numerator,
Should we distribute both?
Or wait, oh,
Oh, wait,
The
wait,
negative?
can't
do we
we?
need to distribute? Oh,
Wait,
no, we don't.
he's
Oh, wait.
subtracting.
I see something cute here.
Oh, can you cancel?
No, we can't cancel, but we can factor this.
We
I
can't.
know.
I think we can,
Take a
yeah.
9 out of the last.
We can take a 9 out of those there.
Okay.
So we can take a 9 out of basically we take a 9 out of the whole numerator. Okay, so check this out. If we do that, we're going to get a 9 times. In the first part, we're going to get e to the 9x minus e to the negative 9x. 9x, that's 9. Times, if we pull the 9 out, what's left? E to the 9x minus e to the negative 9x, the same damn thing.
It's a
So
square.
I'm going to get the square of that sucker there.
Cancel. They're in the top.
No, not yet. We can't cancel yet.
No.
I don't know if we're gonna be able to cancel. We'll see.
Wait, but if you factor in
The
If
the.
I,
minus.
hang on. We gotta write more down. If we take the 9 out there, what's gonna be left?
E to
The same
the
thing.
9x.
Plus, we're gonna have 2 of those pluses. Okay.
What?
So we're gonna have we're gonna have, let's see, minus e to the 9x plus e to the negative 9x.
Where?
Wait, what's the exponent in the
Where?
first one?
Why is
The
it?
even 9x.
That's
It's a
supposed, right
9.
there, that's supposed to be a 9x. I had trouble writing with my pen. All right, try that again. Yes, Stephanie? Yeah.
But.
Is the,
Okay.
okay.
So I'm factoring this 9 out. If I
okay.
take that 9 out, then these two things are identical. They're the
Yeah,
same
but
thing.
I was that for a second, so the top part is also.
Yeah, so I have the square of these two things. Now,
But when you foil this out, you don't
no,
get
no,
the
I'm
same
not
thing.
foiling. Chill out.
I'm
I'm
so
still working on this.
confused.
I'm still working on this. What I have now is the difference of two squares.
If you boil it out technically, it's just the two parts. You didn't.
That means
This is the difference of two
Wait,
squares
wait,
here.
wait,
I have a squared minus b squared, which equals a minus b times a plus b.
Oh, I'm so confused.
Wait, no.
We're
all
This is
No.
red.
You could distribute, but this is an alternate to distributing both those things.
Wait, but isn't that the original?
I don't think this is
Yeah, I
how
don't
this
think this
works.
is-
Yes,
I
this is
don't
totally.
Go
Yeah.
back. Go back one.
This is the difference of two squares.
Go
And
back.
so
go
if we
back.
apply the difference of two
I'm
squares,
gonna-
then we get
okay,
it.
shut up, please. I'm gonna apply this and see what happens. So this is my a right here. That's my a, and that's my b.
Okay.
So then I get e to the 9x minus e to the negative 9x minus b. That's going to be a minus e to the 9x minus e to the 9x.
I thought
Did you
B
want to
was a
distribute
plus.
Right, but I'm distributing the negative through it.
Okay.
So I have to take the opposite of each of those things.
Sure.
Wait,
So that's
Cancels.
so the e to the
so that's a minus b right there.
That's one.
A plus b would be e to the 9x minus e to the negative 9x plus b, which is e to the 9x plus e to the negative 9x. Okay, let's see what this gives us. So here, does anything cancel?
the
E to the 9x cancels. No, but here they're both negative. So I get minus 2e to the negative 9x. That's all of this here. Over here, what happens?
get the same thing.
But I get, that's e to the 9, the e to the negative 9x is canceled. So I get 2 e to the 9x's. So my claim is that's what the numerator simplifies down to,
All of
Okay,
this.
I'm gonna need you to back up a little bit.
times 9.
That's
the numerator. I still have a denominator, which was e to the 9x, let's see, which one was it? Minus e to the negative 9x squared.
Why couldn't we keep it like the other way and cancel out?
You can only cancel things you factor out. There was nothing factored there because that minus in the middle. So what prevented canceling here is this minus right here. So your only other option besides the pattern I noticed there is you would have to distribute, clean that up, and then subtract the distribution here. That's the only other way to do it.
I
A
still,
lot of algebra, no matter what.
If
I still don't understand how you could pull that 9 completely out because it was only in 2 of the 4 things.
Okay, it's, yeah, good question. Let me undo some of that highlighting to make it easier to look at. Okay, so if I factor this 9 out here,
Yeah.
then it becomes a multiple here. So I get a 9 times this stuff. Let's throw it over there.
Yeah, okay,
If I factor the 9 out of here,
yeah.
then I get a 9 times this stuff here.
All of it?
So,
Oh,
well,
because
yeah,
then you
because there's 3
combine
things
it.
multiplied, right?
Okay, yeah, yeah.
Yeah, so then since there's a 9 on this side of the subtraction and a 9 on that side of the subtraction,
Okay,
I could pull the 9 completely out of the subtraction.
thank you.
Okay.
Makes more sense now.
All right, and we are running out of time to do other stuff, so let's see,
do we merge the test tree?
what
Yeah,
does this
or you
give
can
us right
flip it
here?
if you
What
want.
is e to the 9x times e to the negative 9x? What does a negative exponent mean?
Put it in the bottom.
Flip it. So that means this numerator right here is really, let's see, 2 times 9 is 18 times 2 is what, 36? So I'm going to have a negative 36 on the top, but then I'm going to have an e to the 9x over e to the 9x, which is really 1, okay? So that sucker's gone. And then in the bottom, I have e to the 9x minus e to the negative 9x
Which is really just 1 over.
squared, which is really just 1 over the hyperbolic cosine So like William said, yes, the derivative of the hyperbolic tangent is the hyperbolic cosine squared.
No.
Or a relative of, no, hyperbolic secant squared. But it's a relative of it. You get a negative in there also.
No, that's just gonna get you.
So wait, it's negative.
It's
So
negative hyperbolic
the
secant squared.
is the derivative of
the hyperbolic.
hyperbolic tangent.
What's that, Carter?
So how about we all just vote the hyperbolic problem out?
Yeah.
So negative
That's
secant
possibility.
squared.
I vote yes.
I vote yes with Carter.
You don't need to know that formula.
Okay.
Chill out.
But did we just do one giant proof? Is that what that was?
Basically, well, it's kind of a proof, sure. Yeah, we'll go
No.
with that.
Nope, I'm not memorizing that.
Yeah.
We are
Okay,
taking
William,
that
what's up?
poll well. Everybody.
Shh.
Like negative 9 or something around in 3 cents.
Yeah, so if we pulled the 9 out, then yeah, because of the 9 in the numerator, we get a multiple of 9. Because of the 9 in the argument here, we're going to get a 9 on the outside as a multiple. And then the 2 times 2 is related to the hyperbolic cosine, because the hyperbolic cosine, the cosine h, also called the cosh. The cosh of x is e to the x minus e to the negative x over 2. And if you square that, then you get the square of the top over 4. So back here, there's our 4.
So it's 9 times 4.
No, the 4 is part of the hyperbolic cosine. So what we end up right here is the derivative we got is, let's see, so let's write this down. Derivative with respect to x of the, what did we start with? The tangent,
Yeah.
which is also called the tanh. Kind of a weird one.
Ton.
I like to call it hyperbolic tangent better. It's the opposite of the hyperbolic secant squared of x. Now, since we had a 9 here, we would get a 9 there and outside because of the chain rule.
So the answer will always be whatever's inside.
As a multiple, if it's a constant multiple. Yeah. Okay, let's try a different problem. Let's see, number 20 is a similar problem. Hyperbolic sine to the 7th power. So let's see, should we do this the easy way or the hard way? So now you're making me regret I put these on the homework
I mean, that was a goal.
I mean,
Why?
because it's a lot of work.
Yeah.
you put them on the homework.
I did put it on the homework,
You
yep.
thought we wouldn't ask about it?
I know, I thought you would ask about it. I was actually hoping you would ask about it.
Well.
You can't regret now you did this to yourself.
Yeah.
I did do this to myself.
Hey.
If I didn't have a cold today, I would be
Okay,
much
so
more receptive to
The
your
homework
criticism.
isn't liking when you put it as hyperbolic secant. You have to like put it in like
The e to the x form?
no, you have to put it in the 1 over hyperbolic
So you must
cosine,
put it in.
Are you sure?
and then you have to put the like squared on the outside.
Wait, what?
Yeah, I mentioned that's an issue sometimes, that you have to put the square on the outside. So let's
Wait,
see.
so how would you put it in?
Let's try -9. Oh, yeah, so a lot of systems don't accept hyperbolic secants. I don't know if this one does. I've never tried it. So -9
He says it doesn't.
times the
You get it to go?
hyperbolic secant of 9x, and then I have to put an extra parentheses to square it.
A minute. You should have taken it.
Ooh, doesn't like it.
No, it took mine.
How'd you do it?
I just took the parentheses out.
Which parentheses?
The
The outer ones?
yeah, the 7C.
It took that?
Yeah.
Nope,
Mine doesn't.
you got
You
lucky.
must have been special.
Yeah.
Did I make a sign error somewhere? Let's see, where are my notes?
Is
Hand me your computer.
It's taking it weird.
what are those? I don't.
No, I'll see it. Here, take
No,
your-
I don't see a sign error, but it's possible I have one.
Number 19.
Let's see what it really wanted.
What question are you talking
How
about?
come it doesn't have show answer?
That's the question.
It's
Yeah,
9
it's-
times 1 over cos.
Oh, there it is, right there in front of me.
The negative.
Oh, I must have a sign error. It's not a negative.
It's not
It
negative.
should be positive.
Oh, I got a sign error in here somewhere.
It's just-
All right.
I need a second.
So if you make a sign error on a test and you know you made it, or you're not sure, if your work looks like this, start over.
Nathan, how'd you get the?
I don't see my sign error. Okay, we're moving on. I'm cutting my losses. All right, let's see.
Just burned like 3
The 20, or
We didn't burn 3 minutes. That was very productive. Okay. So this is the function we're going to take the derivative of next. Is this the one I want to do?
Yes.
I mean,
Yeah, what do you want to do?
We have to.
Absolutely.
Fine. Okay, so let's see, what do we got? Let's go with this fact that the derivative of the hyperbolic sine is the hyperbolic cosine.
And we know that for suresies?
Yep.
Okay.
So then here, we just have to apply the chain rule. What is the outer function?
something to the seventh.
7.
Something to the 7th power, yeah. So first I have to take the derivative of the 7th power, which is 7 times whatever to the 6th power. That whatever happens to be the hyperbolic sine. Then I have to multiply that by the derivative of the hyperbolic sine, which is
Hyperbolic cosine.
hyperbolic cosine. From the cosh. Oops, the x. And we're done.
We're done?
Okay. You went the easy
That's
way, didn't you?
What's that?
I said you went the easy way, didn't you?
Yeah, did I say do it the hard way?
Oh,
Yeah.
The harder way would be to convert all the EDXs and
yeah.
actually that's not any harder. That's just as easy. Maybe one step more. Okay, let's see. I had a question about from somebody else. 3.7, no, 3.8? 3.7, I think it was. Number 5, was it? Yep. All right, let's take a look. Use exact values, screenshot. You guys help me through this?
Sure.
You can do it in 2 minutes.
Yep. All right, so the first thing we need to know to do this, because we have the chain rule going on here, is just in general, if I only had the arctangent, how do I take, what's the derivative of the arctangent?
Over square root of 1.
No square root. That's sine and cosine have the square
1
roots.
over x
One
minus
plus x
1.
1 plus x squared.
1 plus x squared.
Bring that right there.
That's it. That's the derivative of the arctangent right there. So the only thing we have different here is we have a 7w in there instead. Okay, so how does that affect things? Well, that's just the chain rule, right? So I need to take the derivative with respect to w of the arctangent of 7w. Well, it starts off being the same. The outer function is the arctangent, so I write its derivative down. That would just be 1 over 1 plus.
7w
Yeah,
squared.
this time I have a 7w. Put it in parentheses, please.
And then you multiply by 7.
And then the derivative of the inside is 7, so I have to multiply this by 7.
So really it's just 7 over.
Yeah, so you can clean it up a little bit by writing 7 over 1 plus, and if you don't like the parentheses, then call it 49 w squared. So that would be the derivative of the tangent inverse of 7w.
Oh, that's not bad.
Not too bad. We did it. So again, formulas you need to know. The derivative of the arc sine is what? 1
Minus-
over
1 minus
1 over the square root of 1
1
plus
minus x.
minus
1 minus x squared, yeah.
The cosine is 1 plus x.
x squared.
No, that's not correct.
No, cosine is -1 over
Yeah,
the square root of
cosine
minus
is
x
the only difference is a -1 over. That's the arc cosine. And I just wrote the arctangent down.
We,
Do you need to know our secant or our cosecant or our cotangent?
No.
No, I said you don't need to know those.
Plus.
All right, so you have the choice of either taking the exam tomorrow or Monday. Tomorrow, if you don't take the exam, I'll do another review.
Oh, heck yeah.
And then feel free to send me an email today voting problems off of the practice test. I can't guarantee I will take everybody's input into consideration because that would probably mean there'd be no questions on the test.
just take the 10 that are put on the.
So yeah, so I'll look at what are the most frequently occurring vote off questions.
Are we talking
And I'll
about?
send everybody a
online?
note saying, yeah. So you have until 7 p.m. today to do that.
No, when?
7 p.m.
7
to send me a note voting problems off the practice
Today?
test. Today.
Cinch and
Can you push it
caution
back? I work
touch.
until 9, so I can't.
Okay, you have until, everyone but Daphne has until 7.
We're talking online, right? Not paper, online, the online review.
The online sample test.
Yeah,
The sample test, not the review.
Okay.
Yeah, so this thing here.
Can you,
Oh,
how much time do you have right now?
I got a few minutes.
Can you do one of the ones off the sample test?
Sure. Okay, anyone wants to hang out and do another math problem, please feel free to. I know some of you have someplace else to go. So I'll give you a minute to vacate. Which one?
14.
Oh my word.
And they're just a
It should be easy, right?
Yeah, it's not bad.
So it,
Yes,
is it
so
just,
yeah, I'll keep this going.
is it just 3e to the 30x minus, well 3
Yeah.
e to the 3x plus 3e to the 3x over 2?
Yes. It's that easy. Yeah, so I'm gonna write down what you said. If I can get my screenshot going here. So which one, number 14?
And on the test.
Yeah.
Do you think you're gonna give us the formulas for arc sine, like when, no?
No, you have to know this.
Shoot.
So you need to know arc sine, arc cosine, arc tan. You write this down for arc.
So here, the divide by 2 is just a constant.
Yeah.
It's like multiplying by 1/2, so that's just hanging out. And so I just have to take the derivative of the numerator, which, since it's a difference, I just do one at a time. So e to the 3x, the derivative would be 3 e to the 3x. And then minus, that would be a -3 times e to the -3x. So cleaning that up a little bit, I can pull out the 3, and then otherwise I get e to the 3x plus e to the -3x
Over 2.
all over 2.
And that's just the answer.
Yeah. And so if you recognize the first one as the, let's see, which one is that? The negative, I think that's the hyperbolic cosine of 3x. Then the answer ends up being 3 times the hyperbolic sine.
It's actually originally hyperbolic sine, I think, do.
Let's see, get those signs confused sometimes. We looked that up earlier. Hyperbolic. Oh yeah, the hyperbolic cosine is the plus, hyperbolic sine is the minus. That's right. You should know that.
So when are we gonna learn about hyperbolic?
We'll talk more about them later in the course. Let me see where I made a mistake right there. So you don't need to know those definitions for hyperbolic sine and cosine. But I do expect you to be able to take the derivative of something like that.
Do we have to use like the quotient rule?
No, because 2 is constant. I don't need the quotient rule.
Oh, okay.
So I can just treat that, it just hangs out. It's like, so dividing by 2 is the same as multiplying by 1/2.
Okay.
Yeah, so I just have a multiple of 1/2 hanging out.
I see.
So this is the sine h of x equal to 3x equals 3 times the hyperbolic cosine of 3x. this is what I was looking for here.
It's not too bad.
Not too bad. Try another one.
How about 18?
Okay. Excellent. Okay. And I went over one of those in the video yesterday. There's a couple of ways to do it. Oops. So one way to do it is just have the derivative of an exponential memorized. And so the derivative with respect to x of any base b to the power x is the natural log of b times b to the x. So if you know that formula, that's one way to do it.
And how does the natural log relate to e again?
They cancel out.
So the natural log of x is log base e.
Okay.
Yeah, so it's the inverse function of e to the x. So if we say this was equal to y, that means x equals e to the y. Would be the inverse relationship there.
Okay.
So I'm glad you mentioned that, because this is the other way to think about it. If you know that these two functions are inverses of each other, they undo each other, right? So that means the natural log of anything, let's call it a. Let's see, is this how I want to write this? No, sorry. The natural log of, let's say, e to the y is just y, because e and the natural log cancel each other out.
Mm-hmm.
And you can apply that to this up here. So if you let y equal 2 to the x there, then you can rewrite that as e to the power natural log of 2 to the x. Because what do e and the natural log do to each other?
Cancel each other.
They cancel out, so that's the same thing as 2 to the x. So essentially, you could view this function as 3 times e to the natural log, right? So let me just continue with that. So then I want the derivative with respect to x of 3 times e to the power natural log of 2 to the x. Now, what can natural logs do to exponents? They pull them out as a multiple, right? So that x right there, I can really write it in front of the natural log. So now that ln of 2 is just a multiple of the power. So then here I'm just going to apply the chain rule. So to take this derivative, the 3 is just chilling out. The derivative of e to the something is e to the something. But then the chain rule says I have to multiply by the derivative of the numerator. What's the derivative of something times x? It's that something, right? Derivative of 2x would be 2, the derivative of 3x would be 3. So the derivative of x times the natural log of 2 is just the natural log of 2.
Because ln2 is constant.
It's just a constant, yeah. And then from our previous page, we know that this simplifies back to just 2 to the x. So that's my answer then. 3 times 2 to the x times the natural log of 2. So there's that multiple of natural log of 2 that I said is just part of that formula there.
And
So my advice is memorize this formula. Oops.
which is ln times b to the x.
Yeah.
I got 6x ln 6, 6 to the x ln 6.
No, you can't multiply that 3 into anything. It just stays where it is. So the best you can do to clean up this derivative, back to this page here, would be to say it's 3, oops, nothing simplifies here. All you can do is change the order of the multiplication. So I could say it's 3 times the natural log of 2 times 2 to the x, but the 3 here cannot go inside the natural log, the 2 there cannot go outside. They're all stuck where they are.
3 ln 2 times 2 to the x.
Yeah, that's the best you can do.
I made the mistake and multiply 3 times 2 to make it 6 to the x.
No, you cannot, or that violates order of operations.
Darn.
Yeah, so you can't do that either. Yeah.
It's very
So-
tempting to do.
Can you
Yeah.
not put the 3, make it 2 to the third? Or
No.
can you not do that?
No.
No?
It's just 3 times 2 to the x.
No, I mean, alone.
Oh, I see.
In that
Could you
one.
bring that? Oh, yeah, you could do that. You could reverse that logarithmic rule. So you could write this as the natural log of 2 cubed. Because just like you can take a power out of a logarithm, you could put a multiple back in as a power. Yeah, you could do that. So this would be another answer.
ln of 8 to the 2x.
ln of 8 times 2 to the x would be another possible answer. Yeah, they're equivalent. So just hang on one second, Carter. Yeah, just to double check, you could use a calculator to check the truth of that. If you take the natural log of 8, that's 2.07. If I compare that to 3 times the natural log of 2, it's exactly the same number.
Good. Yeah,
Okay, see you later, William. Carter, you had another question related to that or
No.
something else?
Never mind. Just trying to. So I'm gonna be in LeGrand on Monday.
Yep.
Is there any way I could take the test in like their testing center over there?
Yeah, you could do that.
Okay, do you like have to send something to them or do I just?
You would just tell them you're in calculus at BMCC and they have access to the testing stuff here.
Okay, and what time would I have to take it by there, do you know?
I believe they close promptly at 5. Yes, because I've had students that showed up at 4:30 and expected the testing center to give them extra time and they got kicked out.
Okay.
So you should call to make sure of the time though.
Okay. And
Call
it's-
LeGrand
Well, I'm
and
gonna
say-
take it way before 5.
Yeah.
For sure.
Yeah, but just double check their hours just to make sure.
Yeah, okay. And then